So as I said, at least quickly last week, we're now into the every other week thing. So we had a test last Thursday. This Thursday we will have a quiz, which means tomorrow we'll have the quiz review in the middle of the class where I give it to you. I give you 30 minutes to try it, and then we go over the questions. And then quiz on Thursday. And then next week is the second test. The week after that is a quiz again, the last of the quizzes, and then a little bit of a difference because that Thursday, the next Thursday is the last day of class, I think, and the last test will instead be on the day of the final. And the test will be on the material. So test 1 went through 2.10, which means test 2 will start there. Pretty much chapter 3, about the only thing is there wasn't a word problem from 2.10, so there might be one of those on the test also. And then the third test will be just chapter 4. So it'll just be on the pieces. I did put the answers up on Blackboard, so the answers to the test are on Blackboard. I was a bit lazy. There are 3 versions, but really only 2 sets of questions. So there is test 1 and test 1A, and test 1C is half the questions were from test 1 and half the questions were from test 1A. So I got a little lazy. Instead of writing up the answer for test 1C, all I did is on test 1A, pretty much it's every other question, I said whether the question was on test 1C also. So sorry about that, but you'll have to kind of go back and forth between 1 and 1A if you took test 1C. Okay, otherwise, usual thing, so we started chapter 3 last week. So let me start with homework for that. And 3.1 is just kind of the general idea of how you take the antiderivative, so it's just an idea, but let's do a couple examples. So pretty much just antiderivatives. So one says if the derivative with respect to x is given as that, then it's f. And the notation for that is this, the antiderivative with respect to x. And so what is the antiderivative with respect to x? Yep. And the only little thing is that usually you have the plus c. Here we have to be a bit more specific, since any function that was either just a constant or a function piece that only has the variable y, then its derivative will be 0. That's supposed to be an xc to the y. Same thing. So again, find f. Again, it is in this case, yes, because here they just gave us the derivative with respect to x. So here we're just doing one variable antiderivatives. After 5, we'll do one kind of a full one where you have the double integral. So here, this is, in terms of integrals, this is really just part of it, because usually at the end you're going to get a constant. So after this example, you'll see where that will come up. So this one, just reminding you, and this is kind of a simple example of it, that again, we can have substitution, we can have integration by parts, works the same way. It just looks a little weird because in this case, for example, when you do the substitution, you remember that y is a constant. So you take the antiderivative cosine, which is sine. So this is just like cosine of 2x. So you have the 1 over the constant. Oops. And again, that whole thing. So just a reminder that, as I said, integration by parts, substitution are still valid. Okay, so here's a basic one. So again, it's just the same as the idea for partial derivatives, which is to do the antiderivative with respect to a variable, assume all other variables are constant, and take the usual antiderivative. So any questions on this? By itself, this doesn't really come up. It's really just in the context of an integral, double integral, I mean. Okay, so I jump. So this is more like what you'll see, which is here's now a double integral. And this is a definite integral, which means it's going to give us back a number. Officially, it's in the next section, 3.2, where we're told that this is giving us the volume of the curve below the 2xy e to the x squared over this little rectangle. And kind of the next step, again, there's going to be a substitution because you have an obvious inside function in terms of x. I'll be lazy, just say du instead of the dux. And if I do that substitution, I get this. And this also tells you how you do double integrals. And I did this last week, so I was a bit lazy here, but remember what we're doing is we have an inside integral and we work our way out. So do the inside integral, keep going until you finish. And then do the outside integral. And as you work your way out, you should be losing a variable. So the inside integral is with respect to x, which means after we finish that integral, there should be no x's left, as there aren't here. Probably not. 2.11 really, as I said last week, is a second way of doing the optimization problems. But it's not really helpful for the word problems. So in theory, you could use it when so first it won't be on the quiz. So the quiz will be sorry, I'm thinking of the test. The quiz will be just integrals. But on the test, there could be something from 2.10, which in theory you could use the method from 2.11 to solve. Because I didn't put a word problem from 2.10 on, which means it could be on test 2. So this one, you can see pretty much is very similar to the last one, except we don't have the 2, which means I'm going to get, since I don't have the 2, I have to divide through by it. No, so the tests are not cumulative. So whatever was on test 1 will not be on test 2. Except, obviously you're going to be using partial derivatives, but no questions that are just that. And now going back to the problem, this is, as I said, giving us the volume in some sense below the curve over the region we're looking at. And so therefore, obviously at the end, we should get a number. And as usual, if you want to leave it like this, that would be fine instead of getting a decimal answer. Oh, right. Oh, so I was just being, yeah. So yeah, so y e to the u, the antiderivative is y e to the u, which is y e to the x squared. I kind of skipped a step. Okay. So are the ones from 3.1 I want to look at. Any others from 3.1 that you want to look at? Oh, whoops. Yeah, so sorry, I did miss one. So I plug in the x. I plug in the x equals y, because I should make this, and I get y e to the y squared. What am I missing? Right. So this should be a minus y. So there should be a minus y here. And if I put in the 2, I get 2. If I put in the 1, I get 1. So I should be getting then a minus 1/2. Kind of backwards there. Sorry about that. Except minus 1. So oh, oops. Well, I'm really doing that. It's 1/2, of course. So it should be 3. Sorry, it's 1/2 e to the y squared minus 1/2 y squared. Just the antiderivative of y. Sorry about that. Oh, so this should be and this just has the e to the y e to the y squared minus y. And in some ways, this now does work. It's 1/2 e to the 4th minus e, and then minus 3/2. Sorry about that. So any other questions on this? See if I've made any other mistakes. As I said, any other ones from 3.1 that you want to look at? Oh, the 1/2 so that came from here, right? So I forgot to plug in the 0. So that, oh no, if I plug in x equals 0, I get y e to the 0, which is y. So here there should be a, as I put in later, a minus y. So it came out of the fact that when I first did it, I forgot to plug in the 0. Okay, so any others? Okay. So we did much of 3.2, but I'm going to assume you haven't looked at the homework yet. It was, after all, holiday weekend. So what I'm going to do is just do 2 or 3 examples from 3.2. Then we'll look at homework tomorrow. And also, if you remember from the beginning, means that nothing, well, depending how far we get, nothing beyond what we get to today, remember, is on the quiz. All right, so 3.2. So 3.2 is doing the actual integrals. So this essentially is an integration in R2. So just two-dimensional space. And let me just do view. So what I'm going to do is integrate this function above a particular region. And since this has a few nice regions, I'll do a few of them. So here's 4 regions. I would find that this is the point 1/2 point. And let's integrate over each of the particular regions. So let's start with what will be in some ways the simplest for this setup, the region A. Okay, so over the region A. Okay, so for all the double integrals, you can either set it IDX or dx dy. And the way it works is on the inside integral, you're looking for the smaller to the larger function. Those will be the lower and the upper limits. And then the constants of the outer variable for what that is true. So here in A, and I'm not going to draw on it, but we're looking in here. What we're looking for is on that region A, what is the bottom limit and what is the top limit. And so if I do it dy dx, that's going to be easier. So I need to put that down before you answer the question. So if I do it dy dx, what is the smaller and what is the larger function? So the smaller function is so here's the smaller function, which is y equals x. So we put in x because this tells us that the functions to be right in the inner integral are form y equals something. And then the top curve is, or the bigger curve, is 1 minus x. And that is true for what values of x? Right. So you can see it starts at the y-axis of 0, and it goes to where the 2 cross, which is at x equals 1/2. So in general, this is what it should look like, which is the inner integral is what's the smaller to the larger function, where you solve for the variable that you're integrating with respect to, and on the outside, you're looking for constants. So this one let's actually do, but then the other two, I'll do the two of the other regions. I'll just set up. Although, it's not too bad, I suppose. So I take the antiderivative with respect to y, which is just xy squared. Plug in the upper function, y equals 1 minus x. Plug in the bottom limit, y equals x. You get that. I'll probably want to simplify that to do the integral. minus x quantity squared, of course, is 1 minus 2x plus x squared, and then multiply by x. Obviously, the x cubes in this case cancel. And so I will get and whatever that is, 1/8 minus 1/12. So something like that. So on the next page, I'll redraw this, but just as a quick thing. So the next one I'll do is b. So first, looking at it, what's going to be the double integral over b? And you kind of have to see two different things. So without actually doing the double integral, what are we going to get? The same thing. We're going to get 1 over 24 again, because you can see the region is the same size, and the function 2xy is symmetric around y equals x. So therefore, the values are symmetric around the line y equals x. So it's the same area region, and the functions are equal symmetrically around y equals x. So we'll get the same thing. So before I do part B, because I want to set it up, even though we sort of already know what the integral is, I should say we do need the two things to be true. We do need that it's symmetric around the region, and we do need that the region is the same size. So usually it wouldn't work. So any questions on this before I do the next region? Okay. So this one, let's actually set up two different ways. So let's do dy dx, and then we'll do dx dy, just so you can see we can do it either way. So since we're, again, starting with dy dx, again, we're looking for the bottom and the top function. And why is that a bit more annoying in this case? One's easy. What's the bottom function? Right. But what happens to the top function? Right. So the idea is right here, if I draw a line right here, to the left of that line, the top function is one function, and to the right of that function, it's going to change, which means we're going to have to break it up into two pieces. So to the left of that line, which is from 0 to 1/2, as you said, the bottom is 0. To the left of the line, the top function is x, and then to the right of that, now the top function is 1 minus x. So if the smaller or the larger function changes, you have to split up the integral. Now let's do the same thing, except now let's do it dx dy. And let me ask the same question, which is, can I do it with one integral? So here, does the smaller and the larger function change? And so remember, now we're looking, when we say smaller or larger, y is a constant, so we draw a y equals a typical y equals a constant line. Sorry, my graph is getting messy again. And I'm looking for where does it hit on the left and where does it hit on the right. So what is the function on the left? And now we're solving in terms of x. So the function on the left is x equals y. And on the right, it is x equals 1 minus y. And you'll notice it doesn't change. And the limits, and you can see how this is then going to give the same integral as the last one. Are 0 to 1/2. So either of those is okay. In particular, the second one might be just as easy or quick to do as the first one, because the first one has zeros, which is going to make it easier. On the other hand, we have two integrals. Oh, so the constants are just for what values is it true that the function on the left is x equals y and the function on the right 1 minus y. So you can see it's true from here to there, which is y goes from 0 to the point which is y equals 1/2. Not, well, these two do. So this one and the previous one both get 1/24. And as I said, that's because of two things. One is that the regions are the same area. And second, the function 2xy is symmetric around y equals x, which means the points are going to have the same value on the opposite sides. So just because they have the same area doesn't have the same integral, but in this case it does. And then for c, we're going to get something different. Although I probably won't actually do the integral. So the first one is either direction. So if I look and see this last one, and let me bring it over here, bring it down again as a small version. Will I be able to set up this integral with one integral, doing it either dy dx or dx dy? No, because if I do it dy dx, the bottom function changes. If I do it dx dy, the left function changes, depending on where I am. So any preference between dy dx, dx dy? Since it's higher. Okay, so let me just do it dy dx. And so for that, what we're looking for is where does it change? So here's where it changes. Right. Right, so C is going to be different. And if I drew a line put up here, so for our function, if I did these two regions, the integral would not be the same over those two regions, even though they're similar. Actually, no, yeah, they wouldn't. So those would give us two different numbers because 2xy isn't symmetric around those two numbers. Because 2xy is bigger in region A than it is in region B. So you can, as I said, you can see here is where it changes. So in that region, what is the bottom function? And we're doing dy dx, so right, so 1 minus x. And the top function is x. And now we want to know from here to here, so there's the values for which that is true. Right, so in this case, so in any case, you can always do it either order. In the last case, dx dy worked a little bit nicer. Here, both ones we're going to split up. So what are the limits for x in the first integral, first part, and then we'll have a plus second part. Right, so 1/2 to 1. And if you split it up, there's no reason you have to do it dy dx both times. So for example, and here it would be silly, but I could do the first integral dy dx and the second integral dx dy. As I said, here it would be silly, but you can do it. So in the second region, which is over here, what is the bottom function? And the top function is still x. And this is true over this region, as I showed, which is x goes from where to where. And we can just easily do it dx dy. Seeing if it actually is a bit easier. It's about the same. I guess the difference is that the right function will always be 2, so that doesn't change, but about the same. So any questions on this? Sure. So let's do dx dy. Yeah. So as we said, we're going to split up, so only do the 2. So now my little picture is going to get messy. You can see that where it changes in this direction is right here. Right? Because the left function changes below that line and above that line. So below that line, what is the function and what is the right function? So the left function would be, and we're solving in terms of x, so here the left function is what? Kind of see it? It's right there. One minus y. And the right function is 2. And that is true for y from here to here, which means the limits are 0 to 1/2. Above the line, what is now the left function? Yep. The function is 2, and that is true from this line all the way up to the top, so therefore from 1/2 to 2. And as previous one, either of these would be okay. So obviously you don't have to do it both ways. In this case, I don't think either one's really any easier than the other one. Well, maybe the top one's a little bit harder, but probably not. Usually, they have a couple examples in the text. I forget if I'm going to do one or not. I will definitely do one tomorrow, where doing it one way, and let me just do this in a second. So actually, let me ask about this one, then I'll come back and give you an example where it wouldn't work. So any other questions on this setup? So here's a quick one, which is probably, I'm probably looking forward into some of the homeworks, but that's okay. So let's set this up first dy dx. what would be the limits for dy. Oh, I'm not sure why I didn't put the function. So limits for y would be x, and x goes from 0 to 1. So that's one version. The other version is if I do it dx dy, then now the limits for x will go from the left function to the right function, so y to 1 and 0 to 1. So setting it up, it's easy to do it either way, but now which of those is doable and which one is not? So one of these you can do not too badly, and the other one you just can't do. Which is which? So which one can I do? The dy dx or dx dy? Right, so I can do dy dx because its antiderivative is y e to the x squared. After I plug in, I'll get x e to the x squared, which is similar to the one substitution we did before. So we can do that. On the other hand, e to the x squared does not have a closed form antiderivative. So this one, when I start doing the antiderivative, I can't do it. So in terms of setting up, it usually is about as easy to do it either order, but sometimes for more complicated functions, which you'll usually not see in our class, one order might be impossible, whereas the other one might not be too bad at all. Of course, if, for example, instead of going from 0 to x, I made it 0 to 1 for y, so I did it over the full square, then neither one would work, because eventually we'd have to try to get the antiderivative of e to the x squared, which doesn't have a closed form antiderivative, as in you need an infinite series to write it. So any questions on this? Okay, so let me do another one, except different setup. I'm not sure I'm making the function more complicated because I'm just going to do the setup, so the function doesn't matter much. But let's suppose I give you something like this. I can now ask you to rewrite this in the form dx dy. In some ways, kind of middle of the last one, which is given the limits, you should be able to draw the picture, and then given the picture, you should be able to write it the other order. So the idea is, except for really simple ones, where you have constants, so if the limit for both the inside and outside integral are constants, you can just reorder them. But it should be obvious that here we could not. If I just flipped the order and made it 0 to x squared and 0 to 1 dx dy, that's not going to make sense because we're not going to get a constant back at the end. So that's pretty obviously not the same thing. So I start just drawing everything. So I need y equals x squared, and it's not going to be to scale from the first integral. From the second integral, I need 2 minus x. Yeah, really not to scale. And then I also need the line. I'm going from 0 to 1 and 1 to 2. So 2 is right here. not to scale, this is the 0.11. So make it so you can actually answer a question without trying to draw something, which would be really hard. Here are three sort of enclosed ones. One really isn't enclosed because the axis is imaginary there, so it's not really enclosed there, but let's pretend. And they ask you which of these three regions is the region we are integrating over. Right. So 3 is the region we want because in region 3, from 0 to 1, the bottom curve is 0, the top curve is x squared, and then from 2, the bottom curve is 0, and the top curve is 2 minus x. So as I said, now what I want to do is rewrite it in this form. So the first question is, can I do this now with one integral, or will I again need two? So first little thing, when I say that, you can always break integrals up into pieces, right? Because you can always break up regions into pieces. The question is, do you have to? And here we don't. I put in this line here, which makes it look like there are two regions, but not really, because there's one left function right there. There's one right function. So therefore, we can do it with one. So what is the lower or left in this curve in this case? Right. So I have to solve it in terms of x. So y equals x squared. So x equals square root of y. And the top curve is 2 minus y. And that is true from 0 to 1. As I said, it's not to scale. As I said in the last one, just because this is one piece and the first one is two pieces doesn't necessarily mean the second way is the easier way of doing it, because you'll see in the top one, 2 of the limits are 0, which are going to make that easy. And so it might be about the same. So any questions on this? So let me do one more of these. Oh, oops. So, right, so the idea is we're always going from smaller to larger. And so you can think of this two ways. So let me do just something like this. So let's say this is y equals square root of x, y equals x squared. And really not scale, that's a 0, 0. And it's at 1, 1. Then if I'm doing it, and I'm not going to bother with a function, if I'm doing dy dx, when I do it with respect to y, remember that assumes I'm looking at x as a constant. And if I draw x equals a constant, I get something like that. Of course, I need a generic line. So this is one line, but I need to draw it everywhere in the region. And so when I'm looking for smaller and larger, well, in this direction, smaller means at the bottom and larger means at the top, which means the bottom, the smaller function, will be what I hit at the bottom, which is y equals x squared. And at the top, I hit y equals square root of x. And then the outside limits are, for what values is that true? Here is true everywhere from here to here, which is x goes from 0 to 1. Okay. If I do it dx dy, then now in the inside integral, I'm assuming that y is a constant, which means now I draw a typical y equals constant, which is horizontal. And now smaller and larger means left and right. So I'm asking what function do I hit on the left? So what if I'm moving from left to right, what function do I hit first? And then what function do I hit after? So now I can see it kind of changes, because now the function on the left is the y equals square root of x, but I have to solve it in terms of x. So I get x equals y squared. And same thing here. Now on the right, I hit the y equals x squared, which again, I have to solve in terms of x. And now I'm looking what values of y that's true for, which again, here is that whole region, which is y goes from 0 to 1. So it's always inside is what's the smaller function to what's the larger function, and the outer limit is what's for what values of the variable is that true. It's just that smaller and larger mean different things depending if you're in dx dy or dy dx. And I'll do another example in a second. So any questions on this setup? Here you can see, obviously it's not going to make a difference between the two, because we have the same, basically the same limits. Okay, so another one. And since I'm not going to actually do the integral, I'll just put a fairly simple function inside of it. And again, I want to rewrite this where I reverse the order. So this is dx dy. So I want to rewrite this in the form dy dx. Again, the first thing I do is I want to draw everything. So I have x equals negative y, x equals y. So I'll draw x equals y, or y equals x, whichever way you want to do it. That's in the middle. And y equals negative x. I also have y equals negative 2. And y equals 2. Oops, x goes from 0 to 2. Let me do the same thing again. So there's our picture. I just draw everything. Notice we're not dealing with this function at all because we're just getting the volume under that curve, so we don't care about that in terms of setting it up. So again, let me ask, which of these regions is it? Yes. So it's this region. So let's now do a dy dx. So as with the last one, let me again ask, if I rewrite this, can I do this with one, or am I again going to need two integrals? So how many integrals will I need for this one? Yeah, so I can just do it with one. And so since I'm doing it dy dx, I'm drawing x equal to constant. And so I'm looking, what is the first curve I hit? And as I said in the last one, don't think of just this particular line. Think of a generic line anywhere in that vertical line, anywhere in that region. because if you move the vertical line and it changes your answer, then you're going to have to break up the integral. So what's the bottom curve in this case? Actually, I'll do both. What's the bottom curve and top curve? So the bottom is negative x. Not sure why I gave so much space. And the top curve is, and that is true for x goes from 0 to 2. So any questions on this? Okay. So obviously we have to do more examples because this can be a little confusing if you haven't looked at it before. But I'm going to do it after you try the examples. So over for tomorrow, you're going to look at the homework in 3.2, and then we'll do at least a couple more examples. And so before I move to 3.3, any last questions about this? Okay. All right. So what? So the region that we're looking at. So the region we're looking at is that. Because in some ways, remember when you're looking at these, the axes really aren't there. So the x-axis. So it looks like there's a line there, but that's just imaginary. And same thing with the y-axis. So the x and y-axis are not there unless you're specifically told that, for example, y is equal to 0 or x equals 0. Any other questions? Okay. So the next set is a variation, and we're going to do something similar once we get into triple intervals, which is we did the basic one, and now we're going to do what's called polar coordinates, which is 3.3. So officially, what we were doing before is what's either called rectangular or Cartesian Cartesian coordinates. I'm not sure why I was hesitating on that. And this is going to be called polar coordinates. So let's look at Cartesian or rectangular. So usually, when I have a point, what we imagine is we build an x-axis, we build a y-axis, we put in units, and then for a point, we ask how far along the x-axis are we, how far along the y-axis are we, and that gives us the point xy. So that's the usual way we think of points. But we can do it in other ways. In particular, one of the ways of doing it is imagine we have just the positive x-axis. I can have an origin. I can ask how far from the origin is the point. I can call that distance r. And ask what is, and I'll write this in a second, I can ask what is the angle that that line makes with the positive x-axis. So r will be equal to the distance from given origin. And theta will be equal to the angle it makes in the counterclockwise direction. With the positive x-axis. And that will say that this point is also r theta. And this is polar coordinates. little thing. The nice thing about Cartesian coordinates is if I give you a point, you can designate it with just one number. So if the point is 2, 1, it is 2, 1, and there's no other way of writing it. On the other hand, if I have the point 2, pi over 4 in polar coordinates, then that's the same as 2, pi over 4 plus 2 pi. And that's the same as 2, pi over 4 plus 4 pi, or 6 pi, or 8 pi, or whatever you want. And it's also the same as r in this case says go to the angle and then flip the axis around to the opposite side of the origin. So that's also the same. So in one sense, polar coordinates aren't great because you can designate any point an infinite number of different ways, which isn't necessarily great. On the other hand, if I have a circle of radius 2 in rectangular or Cartesian coordinates, that is this. What is the equation of a circle in polar coordinates? For anyone who's seen this before. That. So the two ways this is nicer is one is, notice this is not actually a function, whereas the second one is. The second one is obviously the second one. The r equals 2 is much easier. So polar coordinates pretty much were made for doing kind of two sets, either circles in particular, or in general things that repeat on a cycle, or some things that are periodic, like sines and cosines sometimes. So polar coordinates are made for circular type stuff in some form. And so this is kind of the background. So let me ask the, actually let me ask it here and then I'll write it on the next one, which is looking at the little triangle I just made here, what's the relationship? What is relationship between x and the polar coordinates? And I'll put here, and then as I said, I'll put on the next page. So if I rewrite x in polar coordinates, what does it become? And y becomes same thing except with a sign. You could then go the other way. So for example, if I divide y by x, I get tangent of theta. So I can get theta is equal to inverse tangent of y over x, but we don't really go the other way, so we don't do it. So let me rewrite that in the next one. So we have here, so x is equal to r sine theta, y is equal to r sine theta, and then what gave us last thing is x plus y squared is equal to r squared. So we want to do this for integrals also. So before we do that, what we need to do is talk about, well, what are we going to get? So let me draw a particular region that we're going to integrate over. I'm not sure why I'm drawing the Cartesian coordinates, but that's okay. So I have a region, and I'm integrating some function above this, so I'm going to get the volume of a function, volume below a function above this region. So in Cartesian, I would break this up into lots of little rectangles. Here, what I have to do is break it up into lots of little changes in angle. And then lots of little changes in radius. then I'm going to assume it's constant on a little piece and get the volume of the little parallelepiped. So let's look at one of these little pieces. Let me bring this over. I have this. I have a little arc. Assume it's perfect. I'm going to have a little change in theta. I'll say d theta. Might want to really call it delta theta, but that's okay. Here is the original r. This is the little change in r. And what I want to get is what's an approximate area of that little dA. A little change in theta times change in radius. And so for that, what I need is what is the length of that little arc on the inside. So I guess let me ask a different question. I'll bring this up, which is if I have yes, so notice the 2 pi's cancel. So in this case, the area is r theta. This assumes that we're in radians. And so here it would be r times d theta. Therefore, the little area dA is about equal to, because we can assume for really small changes that that's basically a rectangle. Will be equal to the r d theta times the dr. So if I have an integral in xy, and I change it to a function in r and theta, dy dx is going to become this r times dr d theta, just reordering for some reason. And this is kind of the important part. We're always getting this r. So if you have a function in xy, dy dx, it becomes that function in r theta times r times dr d theta, which I'll do in a second. So a bit messy here, because this is kind of the background thing, but this is the idea of it. And let me actually do one. So an example, one where we would use polar coordinates. So here's the region I really want to do. So this we're integrating over circles, so it makes sense to do polar coordinates because we know that's going to make it easier. So the first thing I'm going to do is rewrite. So I have 1 over 1 plus x squared plus y squared. So that's going to become x squared plus y squared I know is r squared. Forget that. Let me leave off the right hand for a second. Actually, no, I guess not. Then if I write it in the order dr d theta, I get that extra r. So this is what the dy dx becomes. So the r is always there. And then since it's a circle, our limit should be pretty easy. So our idea is for a particular angle, if I draw a line, what are the 2 radiuses I hit? So the limit would be just from 1 to 4. as just constants. And it's the full circle, which would mean what would be the limits for the angle? It would be that. So pretty obvious that polar coordinates make sense because the limits are constants. So circles under polar coordinates are nice. But so this is kind of the one piece you have to remember, is just you have to get this extra r. And then in this case, that becomes not too bad because I have r over 1 plus r squared. This I can do with substitution. I'll leave off the limits and the outer integral, but it would become, I don't have the 2, so I get 1/2 times 1 over u. Oops. No more integral, except in the antiderivative. And the antiderivative of 1 over u, of course, is ln of u. Right, so this is using this. So in the first part, we're using the polar coordinates, which is that x is equal to r cosine theta, y is equal to r sine theta, which gives us x squared plus y squared is equal to r squared. So that gave us the change. And the r comes in because that's what happens when, from the last slide, that's what happens when we change from dy dx to dx dy, because in a slice, the further away I am from the origin, the bigger the area of the little slice is. So this r times dr d theta is the area of that little piece if I change r by a little bit and theta by a little bit. So it's just always there. And then plug in the two numbers, nothing very nice. Doesn't look very nice, but that's just a number. And then if I integrate that, I'm going to get that whatever that number is times theta. And so therefore, I'm just going to get that number times 2 pi. A little thing which you probably already know, since this is Calc 3, is in the text they probably would have done something like this is equal to ln of 17 over 2 and then the square root of that type thing. And then times the 2 pi. You should know by now, for this class, you don't have to worry about simplifying stuff like that. Oh, it's here. So this is a constant. Let's call it a. When I take the antiderivative, I'm going to get a theta from 0 to 2 pi. But in some ways, the more general thing is if you integrate a constant in one variable, you'll get the length. So that constant times the length. In two variables, you'll get the constant times the area. And in three variables, you would get the constant times the volume of the thing, which we'll get into. But yeah, if you just do it directly, it's just that's a number. The antiderivative, that number times theta. So any questions on this? Okay, so let me do another one. So similar to the last one, let's again rewrite things. So here I have an integral in rectangular or Cartesian coordinates. I'm going to get this in polar coordinates. In some ways, this actually isn't too bad, because if I take the antiderivative, it's xy, which give us the integral x times square root of 9 minus x squared, which we can do by substitution, but that's okay. I was too lazy to make one where it wouldn't work. So we do the usual thing, well, thing we did the last section, which is draw everything. So one of the curves is y equals negative square root of x 9 minus x squared, which if I set that equal to, it gives me partially 9x squared plus y squared is equal to 9. So I'm certainly getting the circle. It's almost a circle. And now the question is, what part of that circle am I getting? And this time, let me do it the usual coordinates. So which, if any, of these parts am I actually getting in this integral? And you read it from here. So this is saying that the bottom limit is the negative, which is, so this is telling us that we're looking only at this part. Because the bottom curve is, if I rewrite it, this is equal to y equals negative square root. And this is y equals positive square root. So I'm just going from the bottom, and I'm only going to 0. And the outside limits are saying we're going from 0 to 3, which means we're only going in this integral. So we're looking in 4. So let's rewrite it. So first let's rewrite x. So x is equal to r cosine of theta. As I said in the last one, we always get the extra r. Rewrite. And now for what values of r? So what are the limits of r? And the nice thing is you can see anywhere in that region, it's the full arc, which means we're starting from 0, we're going to the full radius, which is 3. And what are the angles? And here's where you remember that we're always starting from the positive x-axis and going counterclockwise. So therefore, we're going from 3 pi over 2 to 2 pi. Oh, that's the x. So I said this isn't necessarily any easier, but than the original one. That's okay. So let me do another one. Suppose I have this. So let's rewrite this one. That's inside the exponent is negative x squared plus y squared. This is, without the constants, the two-dimensional normal distribution. So this comes up in probability and error methods and stuff like that. So probability in anything where you're looking at error. And again, I want to rewrite this in polar coordinates. The first one thing is, this is telling us just the whole xy plane. So therefore, what are the limits? R would go from, I'm leaving this off for a second, we'll fill that in a second. So R would go from 0 to infinity, just everything. And it's the whole xy plane, so therefore the theta would go from 0, 0 to 2 pi. Okay, so now let's bring this down. What does e to the negative x squared plus y squared become? E to the negative r squared. And then, kind of an important thing, again, when I rewrite, I get the extra r. So notice in this one, if I try the original one, I can't do it because the antiderivative of, because I can split up e to the negative x squared times e to the negative y squared. E to the negative y squared doesn't have an antiderivative that I can write. And e to the negative x squared with respect to x also doesn't have an antiderivative I can write. So this one, as it is, in rectangular quantities, is not one I can do. This, on the other hand, I can because of this extra. Now, I've done it now twice. This is again one where we left u equal to the exponent, except now it's a negative. And so therefore, skip here. That's going to become a negative 1/2 e to the negative r squared. Trying to fit it on the page, which is why I'm kind of skipping things. But if it's not obvious, remember you can always go backwards, take the derivative. You can get the itself times the derivative of negative r squared, which is negative 1/2 times negative 2r, which becomes r. As r goes to infinity, what happens to it? So as r goes to infinity, what happens to this function? It goes to 0 because I have a negative in the exponent, which means it's in the denominator. So it just gives me 0 minus negative 1/2, so I just get 1/2. And that's going to be 1/2 theta from 0 to 2 pi will be just pi. Really, the normal distribution has this divided by 2, which would make that a 2 pi. But it allows us to get the normal distribution. So this one is a simplified version of something that really does come up and is something we can do with polar coordinates, but we cannot do with rectangular, at least not in conventional methods. So any questions on this? Okay, so I'll do one more to show that in some problems it's not really set up nicely for either of them. Let's do, actually one of these is, since I made the function 2xy, one of them is much better than the other. But let's set this up both ways. And you'll see the setup is much nicer for rectangular. So this one actually, definitely we should do rectangular, but you'll see that there's sort of a problem. So let's do rectangular. Why not 2 dy dx? So what are the limits for the inside integral? So let's start with the easy one. The bottom function is, of course, zero, and the top function is and function. Right. And then x goes from, so you can see that this is to 0, so therefore x goes from 0 to 2. And that isn't too bad. If we took the antiderivative, we're going to get y squared, so we're going to get the square of 4 minus x squared, so it's actually not going to be too bad. But if we had something different, such as the last one, it could get messy. So let's try this set up in polar coordinates. So let me redraw it down here. And you can see this is definitely going to get messy. Just the region R. So same R. Oh, I don't know why it's 0. Thank you. 1 to 2. I'm just being silly. Sorry about that. So the only reason I kind of do this is to show you what really we're doing, because most of the ones you get for polar coordinates, the limits are going to be constants, because that's the whole idea. Is here, if I draw a typical angle, what I'm looking for is what are the two functions it hits. First, let me rewrite it. So 2xy is 2 r cosine theta, r sine theta, and then r dr theta. This is x equals 1. So first thing is we have to rewrite it. So x equals 1 is the same as r cosine of theta is equal to 1. So in terms of r, what is this inside function? Well, basically what I do is solve for r. So I get 1 over cosine theta, or secant. And then the upper limit is just regular circle, so that's easy. That's just 2. Oh, the first line, do you mean this line? Okay, so that is, we want to see what is the smaller and the larger radius. And so to do that, we assume theta is a constant. So it says theta, an angle, is a constant. So I'm drawing at a constant angle just to see what I hit. As I said, usually it's going to be constants, because that's the whole idea. We do polar coordinates because the setup is easier, but just to get an idea what you'd have to do in a more general setting. Right, so r squared is equal to 4, but that's the same as r is equal to 2, because remember, a negative just means you're flipping to the other side, so we don't need both the positive and negative. And the next thing is, now for what values is that true? And you can see, well, it's certainly true starting here, and it goes until I hit this angle. So to make this even worse, I need what is this angle. So I know x is equal to 1, which means y is equal to root 3. So the question is, how do I get that theta? See, I have this little triangle. Make it a right triangle. And I can fill in, well, that's certainly r is equal to 2. Oh, come here. Because I have r cosine theta is equal to 1, which came from x equals 1. I then solve for, since doing a dr, I'm solving for r in terms of theta. So, right, so whichever way you want to do it. So you can do it in terms of, this one is one of the nice ones, as saw it up here somewhere, is pi over 3. But more in general, you could say, well, I know that tangent is equal to opposite over adjacent, so the square root of 3 over 1. So I know that theta is then the inverse tangent of that. Or I know that cosine is equal to the 1 over 2, so the theta is equal to inverse cosine of 1 over 2, or any of those will be similar. Okay. So the one thing is just saying what this problem is supposed to get to you is that, so give me a second, is that polar coordinates are nice for circles. So the circular part of this is nice. The outside circle just becomes the r equals 2. But it's not good with straight lines. So the x equals 1 makes it really messy. On the other hand, rectangular coordinates are great with straight lines, like 1. That gives us just a limit of 1. On the other hand, it's not good with circles. And so it gives us messy things like this, which usually are not easy to integrate. So if you have something like this one, which has both straight lines and circles, it's often not going to be nice in either polar or rectangular coordinates. All right, so back to the limits. So what we're looking for is, where does it hit? So it hits at right here, which is, bring it over to go the whole thing, it hits at x equals 1. But we need that in polar coordinates, so I say, oh, well, that's the same as r cosine of theta is equal to 1. But now for the limit, we need the limit in terms of r. So we need r is equal to something. So I divide through by the cosine of theta to get r in terms of something. And that becomes our lower limit. So it starts with, it's the line x equals 1, which, this line here, yes, okay, so that again is, so we're doing it dr, which means we're assuming theta is a constant. So I draw theta is equal to a constant. Theta equals a constant means I have just a particular angle. So this particular line is arbitrary. I could just easily be drawn it lower or upper, below it or above it. So I just drew a fixed angle. So just to see where I hit. my thing is getting messy now, but the place where it hits the region are those two dots. As I said, don't worry about this too much, because usually the whole point of polar coordinates is we're doing it so that it's nice. So if we're getting something like this, well, it's kind of silly. We might as well have stayed with the rectangular coordinates. There are a couple cases where you still want to use polar coordinates, but really the whole point of polar coordinates is to make it some function easier. Yes, but usually one of them will be obvious. So for example, in the previous problem, you can't do using rectangular coordinates, so you're definitely going to want to use polar coordinates. And in general, if you see just circles for the region, you're going to want to use polar coordinates. So often it is true that if something is easy in polar coordinates, it's difficult in rectangular coordinates and vice versa. So usually, so in theory, you can always do either one. It usually will be much easier in one version. Okay, so any other questions on this, knowing that the whole idea of this is to show that we can make one that's kind of mixed, that's going to be hard in either case. Okay, so I was going to quickly start 3.4 to do the usual thing, but in a few minutes, and we didn't do the usual break where you actually try a problem. So I'm going to stop here. So for tomorrow, look at the homework for 3.2. This is 3.3, which we've done much of it. So this definitely could be on the quiz. So start looking through the homework for 3.3 also. And so the quiz will be 3.1, which is just basically antiderivatives, 3.2, and perhaps part of 3.3. So okay, the usual thing, if you are then don't have any questions, we are done. I'll see you tomorrow. As I said, quick thing, if you only submitted the test to me, if you email me, I will email you back the graded one. It looks like the TA hasn't finished grading yet, so sorry about that. So otherwise, see you tomorrow. I'm going to stop recording.